we will discuss why we need to study semiconductors. Because we are saying semiconductors, intrinsic semiconductor, extrinsic semiconductors. So why we need to study these semiconductors? Because they have very vast potentials to be used in the electronic or the electrical devices like computers, mobile phones, radios, even the chips they are using. Semiconductors are being used in every electrical and electronic devices. You know, if you have any solid which conducts electricity, maybe due to the semiconductors or maybe due to the metals, because we know that metals are also good conductors of electricity. We are studying here the semiconductors because semiconductors they behave as a insulator at 0 Kelvin, because we know that in case of semiconductor we have a conduction band and the valence band. This is the conduction band and the valence band. So we know that there is energy gap between these bands. In case of valence bands, all levels are filled, and in conduction bands, all levels are empty. So at 0 Kelvin, we have so much gap between these valence band and the conduction band. So no electron is free to move. So when there is no electron free to move, so that means it do not conduct electricity. But this is the case when you are talking about T equal to 0 Kelvin. But what happens when you have T greater than 0? So in that case, we see these electrons can go from this valence band to conduction band. So firstly, they are in the valence band, they do not conduct electricity, but as your temperature is greater than 0 Kelvin, so these electrons can move from valence band to conduction band and they are free to move inside the semiconductor and they conduct electricity. We are studying these semiconductors and these are very useful in the electronic and electrical devices. Before semiconductors, we use vacuum tubes, and even vacuum tubes are very heavy and even they are very noisy. So in replace of these vacuum tubes, we use semiconductors. When we use these semiconductor in the electronics, they are very fast and reliable and they have very small size. So in the daily life, you see every appliance has a semiconductor. Semiconductors conductivity is between conductors and the metals, but they are more useful as compared to these two materials. Semiconductors are very important materials that are used in the electronic and the electrical devices, because the current conduction is due to the presence of two type of the charge carriers, electrons as well as holes. Because in case of non-equilibrium states, recombination is not going there, and in that case, what's happening? They constitute the current because we are applying electric field. They are going to the positive terminal of the battery, and holes are going to the negative terminal of the battery. When you are giving energy to it, these electrons are going from the valence band to conduction band, and this is the charge generation in the semiconductor, and we name these generation rates of electron and holes in the semiconductor as Gn and Gp. Rate we are saying that is at how much time, how much number of electrons are generating. So this is the generation rate of electrons, and when you are talking about the holes which are generated due to this thermal energy, so that is the generation rate of the holes, we named it as Gp. So these are the carrier generation rate in the semiconductor. So you can see figure at T equal to 0, there are covalent bonds and no free electron is there. But what happens when T is greater than 0? Their bonds breaks. We can say that the valence electron, those are present in the silicon at the T greater than 0, they can go from valence band to conduction band. So they are free now and a hole is generated in the valence band. So we get the charge carrier generation. Depending upon how much number of electrons are generated or how much number of holes are generated, so we have generation rate of the electrons and the holes. And we know that if you have not applied any electric field, so what will happen? So there will be possibility that these electrons and holes again recombine, because they are moving in the random direction now, because when you have not applied any biasing, so when they are moving in the random direction, so there is possibility that they can recombine or they can go back to this ground state. Charge recombination also takes place. In case of p-n junction, we see holes are present in the valence band, electrons are present in the conduction band in n-type case. but there is some potential barrier. But when potential barrier is removed, so these electrons now moving from the conduction band of n type to p type, and they again recombine to whole of the p type. This is the carrier generation in the semiconductors and the carrier recombination in the semiconductors. So now we will find out the carrier concentration in n-type and the p-type semiconductor. For that we are considering here the equilibrium state of semiconductor. Equilibrium state of semiconductor means we have not applied any electric field. So what's happening in this case? In this case, total charge density in the semiconductor will always be equal to the negative charge density. Means if suppose you have a semiconductor here, so it could be silicon or it could be germanium, and we know that there are valence band and the conduction band, all levels are filled and conduction bands levels are empty in case when you have temperature T equal to 0. But what happening at T greater than 0, those electron can now go from valence band to conduction band. If one electron is in this conduction band, so one hole will be there in the valence band. One more electron can go. So that means the number of electrons and holes you can see here are equal. That means positive charge density is equal to the negative charge density. Semiconductor is neutral. Free electron and the holes, they obey the law of electrical neutrality, that positive charge density is equal to the total negative charge density. But what happens when you are adding impurities to it? So if suppose you are adding donor impurity. So what is donor impurity? When you are adding pentavalent atom to it. So that is a donor impurity. So in that case what happens? We have an extra electron. If suppose you have added only one impurity to this semiconductor, the number of electron concentration we are taking N, and the number of hole concentration we are having P. If you have added acceptor impurity to it, we are having the hole concentration and the electron concentration. So these are four quantities we are considering in the semiconductor here. If you have intrinsic semiconductor and you are adding donor impurities to it, so you have ND number of donor atoms, and when you are adding acceptor impurities to it, so we have this concentration of acceptor atoms. And we know when you have T greater than equal to 0, number of electrons are there, number of holes are there. So what the concentration of holes and the electrons are in the semiconductor? So we are saying hole concentration is P and electron concentration is N. And according to the law of electrical neutrality, we say that Nd plus P is equal to Na plus N, because we are saying that number of positive charge carriers, those are equal to number of negative charge carriers. So in that case some of these terms should be equal due to law of electrical neutrality. And now we will discuss about here the n-type semiconductor here. So it should be kept in mind that we are talking here the equilibrium state of the semiconductor. So equilibrium state means we have not applied any biasing. When you have not applied any biasing to n-type semiconductor, because in case of n-type semiconductor we add only donor impurity to it. If suppose this is the intrinsic semiconductor and you have added this donor atom to it. So when you added donor atom to it, now it will be a n-type semiconductor. So in case you are only considering the n-type semiconductor, so there will be no acceptor atom. We have added just pentavalent atom. In case of n-type semiconductor, we have majority carriers electrons and minority carriers holes. This term is very large as compared to P, because N are the majority carriers, P are the minority carriers in case of n-type semiconductor. So this is equation now that N is greater than P in case of n-type semiconductor. So you can neglect this P as compared to N, and D now equals to N. According to law of mass action, that number density or the concentration of holes, when you multiply it by the concentration of this electrons, product is constant, and that constant we say it is Ni square. So you can calculate that when you have added donor impurity and you want to find out the carrier concentration of holes, So you can calculate, and N is here the donor atoms you are adding. So in case of p-type semiconductor, which impurity we add? In case of p-type semiconductor, we are adding acceptor impurity. So Nd equal to 0. So Nd is 0 in the law of electrical neutrality equation. In this case, P is greater than N. So you can ignore this N as compared to P. So when you are ignoring this N as compared to P, so you will get Na equal to P in case of this p-type semiconductor, and earlier it was Nd equal to N. Now it is Na equal to P. In p-type, concentration of acceptor atoms are equal to the concentration of free holes, and using the law of mass action, N into P equal to Ni square. So firstly we say how many number of atoms you have added, so that will be equal to hole concentration. So if you want to find out what will be the electron concentration, you will use this formula.